Welcome to Easy BTech, your guide for BTech and beyond. In the today's lecture, we will discuss regarding Bjt configurations. Okay, students, these Bjt configurations are classified three types. They are common base configuration, common emitter configuration, and common collector configuration. These three configurations we will discuss today, and we will obtain their input output characteristics. What is their graph? Input output characteristics. Okay, students, we will start it. Okay, in the previous lecture we discussed about configurations, common base configuration. In a common base configuration, base is common between input and output terminal. Now you can see. Now this is grounded. This terminal is a base. This terminal is an emitter. This terminal is a collector. Okay. Now it is an NPN transistor. Now here the input side current is IE and the output side current is IC, and the voltage in between this VEB, and the voltage here VCB. This operated. This voltage we will call as a VBB, and this voltage VCC. These are common base configurations. Now you can see here the base is this terminal will call as an input and this will call as an output. Base is common between input and output terminal. Now you can see from this if you write the two port network parameters, that is V1. What is the equation for H parameter? V1 is equal to H11 I1 plus H12 V2. Next I2 is equal to H21 I1 plus H22 V2. From this V1 is nothing but this voltage we will call as a V1. This voltage we will call as a V1, and this current we will call as an I1, and this current we will call as I2, and this current we will call as a V2. Now from this expression V1 is nothing but VEB is equal to H11 is nothing but we will write as H I input, it is a base configuration, HIB, I1 is IE plus H12 HRE HRB V2. V2 means output voltage VCB. Next output current IC is equal to HFB IE plus H0T VCB. Is an equation 1 and it is an equation 2. From this We will write from the previous lecture we have studied that V1 is a function of I1 comma V2. Now to study the input characteristics, V1 is a function of I1 where V2 is constant. V2 is constant. Okay, from this graph we will draw the characteristics. Now you can see VEB is equal to HIB into IE. We can obtain the value of HIB is equal to change in VEB by change in IE. This is the value of HIB. This is known as input current, input voltage, input current. This simply will call as an input resistance. Input resistance or input impedance. Okay. Now, therefore, configurations, BJT configurations are classified depending upon input and output characteristics. Okay. Now, if you take input characteristics, means V1 is a function of I1 constant of V2. It means we can plot, we know that we can plot a graph, between input voltage V1 and input current I1. Okay, we can plot a graph between input voltage I1 and input current I1 by keeping output voltage V2 constant. Okay, now in the previous you can see to study the input characteristics of the common base. Now you can clearly understand we are keeping this VCB constant. By varying this VBB, we note down the value of IE and VEB. Okay, students. Okay, by changing the VCC, we can make the value of VCB constant. Then, by increasing the value of VBB, we can note down the value of input current and input voltage VEB. Okay. Students, that is we got that the function VEB is equal to HIB into IE. By keeping output voltage VCB constant, we can plot a graph between input voltage VEB versus input current IE. Remember, this is the point. Now it is like if you see the diagram here, Now you can see here you are giving negative connected to the n-type material. It is a forward bias. It's like a emitter base junction. It is emitter base collector. Now here when this JE junction is operated in forward bias, the current across the junction, it is NP. It means it is like a PN junction diode. Okay, students. Now if you plot a graph here, it's like a PN junction diode. It is similar to PN junction diode forward bias characteristics. Forward bias characteristics. Okay, this side is IE current, this side is VEB. Okay, now initially you will get the graph. Okay, you will get the graph like this. This is at VCB 1 volt, VCB 2 volts, this is VCB 1 volt, this is VCB 2 volts, VCB 3 volts. Okay, now you can see by keeping you will get by keeping the output voltage VCB constant, we can plot a graph between IE versus VEB. Okay, this is the input characteristics. Suppose if you want to find the input impedance HIB, that is you can take any point. This is a one point and this is another point. This difference we will call as a VEB 1, VEB 2, and it is IE1, IE2. Now we will get a change in VEB by change in IE. Either we will find the value of HIB value. These are input characteristics of the common base configurations. We will plot in this manner. Similarly, if you study the output characteristics, output characteristics, output characteristics, output current I2 is equal to function of I1 comma V2. Now here I2 means IC is equal to HFE IE plus H0 E VCE VCB. It is a base configuration HFB. Okay, this is a second equation. We know that to study the output characteristics, what we are going to do? By keeping input current constant, by keeping input current IE constant, by changing VCC value, you can note down the value of IC and VCB. Okay, means we will write IC is equal to H0B into VCB, keeping input current constant, input current constant. Input current is IE. Okay. Now, okay, we can plot a graph. We can plot a graph between IC versus VCB, IC versus VCB by keeping IE constant. IE constant. Okay, and the graph may be in this manner. IC, VCB. Okay, students, this region is known as an active region. When transistor is in active region, the graph may be like this, and this region from this region is known as saturation region, and below this region is known as cutoff region. Cutoff region. We have clearly studied this region is a saturation region, this region is an active region, and this region is a cutoff region. It means in this mode both are in on state mode, and here on off mode, and here both are off mode. No current flows in the cutoff region. Okay, students, so this is about a common base configuration circuit. This is about common base configuration circuit. Okay, students, similarly, we will discuss common emitter configuration circuits. Now, similarly, if you study their region of convergence, suppose cutoff region. What is cutoff region? This is a cutoff region. The region, okay, the region of the graph, the region of the graph which lies below IE is equal to 0. The region of the graph which lies below IE is equal to 0, and the right of VCB 0. This region is known as a cutoff region. It means in this you can clearly study the current IE is equal to 0, and VCB is 0. VCB 0. VCB greater than 0, that is IC 0. This region known as cutoff region. Cutoff region. Now in the previous you can see clearly, in this graph you can clearly see, here for IE it is, we can get IE1, it is IE2, it is IE3. We are getting the three graphs. It means how we can get? By keeping the input current constant. Okay. Here you can see clearly, first initially by changing the value of VBB, we can keep this IE at 1 milliampere, by keeping at 1 milliampere constant. Now go to the output VCC. By changing VCC, you can note down the value of IC and VCB. IC and VCB, then we will get a graph between output current versus output voltage. These plots are drawn. Okay, we will draw in this manner. I at 1 milliampere, it is at 3 milliampere, it is 5 milliampere. By taking the IE value constant, we will get a graph between IC versus VCB. This is what is the region, the cutoff region means the region of the graph which lies below IE is equal to 0 and right of VCB, that is in this current IE is 0 and the collector current IC is also 0. It means both are operated in reverse bias. Both are operated in reverse bias and the current through the transistor, that is IC is equal to IC naught, is in case of nanoamperes for silicon, microamperes for germanium, which is a negligible current, in an cutoff region. The current through the transistor is a negligible current, that is IE is equal to 0, IC is equal to 0. Okay students, next region we have, that is saturation region. Okay, next one is saturation region. In this saturation region, what you can see, both are made in forward bias, that is JE junction. JE junction is nothing but which is between emitter to base. This emitter to base junction is operated in forward bias. That is saturation. Okay, simply we will say region of the graph which is operating above IE is equal to 0. Above IE is equal to, in the previous diagram you can see. Now this is a saturation region. It means the current, this is the current IC. It means it is above the zero current. Okay. Is it clear? Okay. In the saturation region, we will call this IC current output current. IC current varies with respect to IE versus VCB. Okay. This region is known as saturation region. Now you can clearly see this is this region is a saturation region. These all are the IE values, IE greater than 0. By keeping IE constant, we can plot a graph between IC versus VCB. Okay, it means this region is a saturation region. Saturation region is nothing but the current through the transistor, that is IE is operating above the 0. IE operating 0 means in this region only if IE operates, 0 axis only. If IE is greater than 0, definitely IC current varies, this IC current increasing in IC current. Now this due to increasing of IE, see how the IC current is increased. IC current, that is IC current increased with respect to IE versus VCB. That region is known as a saturation region. Next, we will see the active region. Active region. In active region, we will make that is a constant. That is region of the graph. Region of the graph which lies above IE is equal to 0 curve above, region of the graph which lies above IE is equal to 0 curve, and left of the left means you can say this from this statement you can write. Now this we will call as a okay. Now you can say this region is a saturation, this region is a cutoff, this region is an active region. If you draw the graph, IC versus PCB. Now you can see this constant, this up to here the current increases, that we will call as a saturation. Here the region of the grass above, this all are IE. The region of the graph which lies above IE curve, which side it is? Right side. IE 0, the curve right of the VCB. Now it is VCB, now this is right side, this is left side. Right side of the curve. Here similarly you can see in this region IE greater than 0. IE greater than 0 means IE is in forward bias. IE is in forward bias. Next, VCB greater than 0. Okay, that is IE, that we will call the collector current. VCB greater than 0 means now it is in reverse bias. VCB greater than 0 means reverse bias, that is IC in reverse bias. Now an active region is nothing but JE junction. JE is in forward bias and JC is in reverse bias. Now the transistor operated in this region, then it is known as an active region. Okay. This is about transistor configurations, common base configuration circuit. Okay, students, you can clearly understand here. This is a common base configuration. This is, we are using a transistor BC107. Okay, emitter, base, collector. Base is a common between input and output terminal. Using H parameter two-put network analysis, we will write these expressions and we will solve all these expressions. Okay, students, this is about Okay students, this is about a common base configuration. In the next class we will study about common emitter configurations. Thank you.